We're going to dive into this a little bit more today, Faraday's Law, and maybe do some examples in terms of generating the CMF. So just as a quick reminder, this is our definition of magnetic flux. So it's the amount of magnetic field strength, well, not the amount, but it's the magnetic field strength passing through the area of a loop. We've got a dot product, so it tells us that the direction matters. And so we're going to address all those things. So strength, area, direction. And that what Faraday and Henry figured out was that the EMF, the voltage, you could say, the EMF produced by this flux passing through an area occurs due to its change. And so this is a time derivative. And so that means if we have a constant magnetic field, a constant angle, and a constant area, all that stuff would be zero and we'd have no EMF. But if we've got a changing magnetic field over time, we get an EMF, or a changing area over time, we get an EMF, or a changing angle over time, we get an EMF. So we've got to have 1, 2, or 3 of those different values changing in order to produce an EMF. And so what we'll do today is just kind of look at some kind of simple examples of that. So let's start with the magnetic field strength. So let's imagine for a second that we've got a loop that's got a specific area. So let's say we've got this loop like this. And let's say that this area of our loop is a constant value. And what we'll do is we'll place a magnetic field. It's going to be parallel to the area vector for that loop, like so. And let's say that our magnetic field strength is a time-dependent magnetic field. So let's just say that our time-dependent magnetic field is some constant. Let's call it, let's say B rho. We'll call it B1, I guess. B1 times T. All right, so that's very simple. So what's happening here is as time goes on, the magnetic field strength increases. So if we were to look at magnetic field versus time, we've got a nice straight line like that. So it's getting stronger and stronger and stronger over time. We've got no change to the angle. Our A and our B are in the same direction, although I didn't label it my B here. And so let's see what kind of EMF is going to be produced in this loop. So all we have to do is apply Faraday's law here. So we'll find our magnetic flux first. So our magnetic flux is going to be our integral of B dA. We said that our A is in the same direction as B, so it means this becomes a cosine of 0. We're going to integrate dA, so this quantity becomes BA, like that. And since B is equal to B1 times T, we get B1TA, just like that for our expression. So now we can apply, figure out our EMF, which is equal to negative the time derivative of our flux. And so all we have to do is do negative the derivative with respect to time of the quantity B1TA. And again, said we'd start off nice and simple. So if we do the derivative of the B1's a constant, A is a constant that comes out, we do the derivative of T, that disappears. And so what we find is our EMF here is equal to negative B1A. Would be our expression for EMF. Now, if we want to play with the units, we can do that in a couple minutes. But our quantity, this constant B1, couldn't be Teslas, right? Because in this particular case, it would have to be Tesla seconds in order to do that. But we've got a nice simple EMF here. So if we knew what the constant B1 is and we know what A is, that'll tell us the EMF produced in that particular loop. And anything that we could do, I mean, we could certainly do something more complex. We could have this magnetic field changing, maybe something like that. And so we could turn this into a T squared relationship. That would just turn this into a T like that. And that would show that our EMF would be changing over time. So the example we did here, we'd have a constant EMF over time. It would look like that. And for this curved magnetic field changing over time, obviously we'd have an EMF over time. That would be increasing over time. So that's how we use Faraday's law, and we think about it in terms of the time dependence. If we have some sort of time dependence, we get a nice expression like that. Now, let me see if I can draw for you or come up with an expression where maybe it'd be a little bit more interesting. And so this is one that I've seen before. Let's say that we've got a magnetic field that's a constant that looks like this. Okay, and we'll say it's a constant just to remind ourselves. So we've got a constant magnetic field. X's are into the paper here, sitting like that. And what I'm going to do is I'm going to take a loop of wire. I'll put a little resistor on here. Oops, this resistor never dropped. There we go. A resistor on that loop of wire. I'm going to drop that loop into our magnetic field. You know what? We'll make it easy to start with. Let's just say that this is horizontal, just like the paper is. Let's just give it a constant velocity. We'll start easy like that, and then we'll drop it later. So I've got a constant velocity. I'm going to take this loop of wire. I'm going to move it into this section. And let's say that this distance here is the quantity A. We'll think about this distance here as being the quantity B. So we've got a loop, a rectangular loop here. It's got some resistance to it. It's got a side A and B, and it's got some velocity. We're going to move it at a constant velocity into this magnetic field. And why don't we ask the question, how much current is flowing in that wire? Like that. Well, we know for current, we're looking at Ohm's law. We're going to have to assume that everything's ohmic here. So current would equal to our epsilon divided by R. So basically, we're going to have to do Faraday's law to figure out our epsilon, just divided by R. And so that's the simple step at the end. But we've got to figure out all the other stuff here. So let's start off with figuring out what our magnetic flux is. So our dA, that's the area vector. And our area vector, we could have it coming up like this. We could have it going down. Doesn't really matter in terms of this. That's just going to give us some information about the direction of the current flow. So we're going to use Lenz's law to do that anyway. So I'm just going to make my area vector also be an x, like that. But what we notice, hopefully, is that my area vector is going to change. Right now, the amount of area that's actually inside the magnetic field, where this little straight line is, it's not the whole loop, just a portion of it. And so that means over time, the area is actually increasing. So the B is a constant in this case, but our dA value is changing. So let me see if I can write some sort of expression for the area here. So the area that's enclosed, A is a constant value, but this distance here is going to change. So let me call that distance x, I guess. There's a lot of x's on the paper, but the distance x. So my area vector here is going to have to do with the quantity x times the quantity little a. And x is a distance, and that distance is going to change with my velocity. And so if I think about the distance, x would just simply be, since the velocity is a constant, velocity times time. And so I can plug that into here, and so my area is really the velocity, time, and the distance a. And so when I do my flux, that just becomes BA, because the dot product's the same. My magnetic flux is going to be B times A, which is now B times VTA, like that. And now I should be able to figure out my EMF. My EMF, which is equal to negative the time derivative of my magnetic flux, is equal to negative the time derivative of my quantity BVBVTA, like that. And again, we do the derivative, B is constant, V is a constant, A is a constant, so just the T disappears. And so we get an EMF here of negative BVA. We know the current is equal to EMF divided by R, and so our current here is going to be negative BVA divided by R. That's my expression. Now again, the negative sign is kind of meaningless to us. We want to think about Lenz's law to figure out the actual direction. So we'll use real current flow here, and what we know about Lenz's law is that the magnetic field created due to the induced current will oppose the change. So right now there's two X's, two green X's drawn inside my loop. And so as this loop moves down, it goes from 2 to 4, and it keeps going down. It goes from 4 to 6. And so as this loop is moving in this direction, we're growing x's inside. More x's are propagating. And so what would change that would be dots, right? So that means a dotted magnetic field, I'm going to call this the induced magnetic field. That dotted magnetic field is opposing growing x's. So if there's 2 right now, when I come down here and I end up with 4, if I put 2 dots in here, those 2 dots will cancel off 2 of the x's, so therefore opposing the changing magnetic field. And so again, using my left-hand rule, because we're using real current flow for this, I point my thumb up at the camera, I wrap my fingers around, and so that means that the current induced in this loop is in that direction. And so if I wanted to kind of put a topper on this, let me redraw my picture here. For, we'll call this the V external. We'll put my loop here, like this. We'll say it has some velocity in that direction. What we know is that we're going to end up with a current that's going to flow clockwise here. So that's going to be our I induced. And our I induced is equal to, let's see, BVA over R. And I dropped off the negative sign because my picture is telling me which way it flows. So if we take this loop and we shove it down in that direction, we're going to get a magnetic field strength that's equal to that much. So if I shove it down faster, V gets up, we get more current. If I make this A quantity, so the area of the loop bigger, so this distance, make that bigger, I get a more induced current. If I strengthen the magnetic field, I get more induced current. And that's all experiments that we did last year. Last year when we played with our, during Magnet Mania, when we looked at our little coil of wire, it was a solenoid like this, and we shoved our magnet in. Oops, it's supposed to be north. We shoved that thing in slow. We got a little flicker on our ammeter. But when we shoved it in fast, we got big movements. And so the higher velocity, more current. So, and again, in this case, sort of the opposite. We could imagine shoving that in. That's what's happening there. That loop's being shoved into that magnetic field. Okay, so we've looked at time-dependent magnetic field. We've looked at an area-dependent magnetic field. Again, pretty simple ones, but generally speaking, that's in the case. So the one that we have to look at now is we have to look at what happens when the angle is changing. So I need to, create some sort of situation where we've got a changing magnetic field in terms of angle. So let's say that I've got my loop here, like this, and let's say that my area vector for my loop is pointing in that direction, and we'll have my magnetic field external, say something like that. And what we'll imagine here is that we're going to change this angle. So let's see. So that's just some sort of reference position. And we'll call this the angle phi, like that. So the angle phi refers to the angle between this reference position, which happens to be collinear with A, and the magnetic field. And so what we'll imagine is this magnetic field is going to rotate around, something like that. And so let's say that phi is time dependent, so we'll just call it, say, beta t. So beta is some constant value. Again, this can give us a nice simple one. We could make it more complex, could make it constant squared, say we're speeding up the angle or something like that. And so all we'd have to do then, just like we've done over and over and over here, we find our magnetic flux, integral B dot dA. So now we're going to put that cosine function in there. And so this is going to be B A cosine looking at phi like that, and phi is going to be beta tau, or beta t rather. And then we'll find our EMF, which is equal to negative the time derivative of the magnetic flux. So we're going to do the negative, the derivative with respect to time of our quantity BA cosine of beta t, like that. When we do that, we take the derivative of the cosine function, we get the sine function. We're way too big here. But what we find is that our EMF is equal to BA, C. The beta would come out, sine of beta tau. Now, beta is a constant, B is a constant, A is a constant, and then we've got a sine function like this. And so what we'd find is that our EMF over time would be varying like this. So our other pictures that we've looked at, and our current would follow the exact same thing. So if we divided this by resistance, it would just be the exact same shape. So what we're getting here is if we were looking at my loop, let's say, draw my loop like this. Hopefully what you notice is that this EMF drops in the opposite direction. So that means the current's oscillating. The current's going this way for a little while, and then it's going this way for a little while. And at some points, here and here and here and here and here, it's at zero. And so this looks, to me, a lot like what we would call AC current, or alternating current. So if we take a rotating magnetic field, and of course we could rotate the loop as well, but either rotating the loop around or rotating the magnetic field around would produce this type of EMF. And if you think about it, that's what a generator does, right? If I've got, say, a little propeller here connected to, let's put a magnet on it, I guess. And then I've got a coil. Like that. If some wind or something blows in this direction, causes the propeller to spin, it's going to rotate this magnet. That rotating magnet is now going to change its magnetic orientation with respect to the coil, and it's going to produce my AC signal. And so this would be a really simplistic looking generator setup. So we could rotate the magnet. We could do the same thing. We could make the magnet stationary. We could rotate the coil. But either one is going to have a changing magnetic field, the angle of which is going to change, and that could produce a signal, something like this. Okay, folks, so there's Faraday's law, some examples of it. What I'll do, I'll try to give you a couple mathematical examples, maybe a couple AP questions, but the big idea is figure out what's happening to the magnetic field in the area, which is typically going to be BA. If there's an angular change, we'd put the angular change in. If there's a change to the area, like with our dropping or moving video, we could change it there, or just simply putting the time in. Okay, everybody, have a great day. See you soon.